Okay, so my name is Noson Yanofsky. We're in the class is called the Outer Limits of Reasoning. We're up to chapter 5. We did part 1, 2, and 3 already. This is part 4, which we're going to talk about section 5.3 here. And I have to say, this is probably, and I warned you about this before, this is probably the hardest section of the book that we're going to be covering in the class. So it's important that you see it and you understand it. It's brand new concepts that you've never seen before. You've seen hard problems versus easy problems, but this is going to be a new problem, a new idea. We're going to compare problems, and you'll see in a second. So last time we said as follows: we had these easy problems in section 5.1, then we went through 5 hard problems in section 5.2, and we explained them and we showed why they're considered very hard problems, and then we finished off section 5.2 saying, you know what, maybe there's a better way of doing it, okay? Maybe there's faster computers, and we saw that faster computers are not really going to help you with this. Multiprocessors, having many computers working on the problem, it's not going to help you with that. And we saw something like if you had 10,000 computers working on a problem, which takes trillions of centuries, 10,000 times faster is not really going to help you much. Okay? I just want to say something I didn't say back there. It's in the book, I think. It says as follows. Physicists tell us that there are 10 to the 80 particles in the universe. Not on Earth, not in the solar system, in the universe. I don't know how they figured this out. They have some idea of how many solar systems there are, how many Milky Ways, how many different systems there are, and they have some type of number, and they multiply and multiply and multiply and come out to 10 to the 80 particles. Just imagine that's 1 with 80 zeros afterwards. If every one of those particles was working on the problem, let's say you're a traveling salesman problem with 100 cities, still you would not be able to get a good answer. Okay? And I go through the numbers in the book, and I go through it very carefully, how long, it would still take trillions of centuries for you to solve the problem. So having not 10,000 processors, but every single particle in the universe being a processor still doesn't help you. A third possible example thing that could help you is quantum computers. Very important book to buy. It'll make you happy, etc., etc. Okay, but we said even quantum computers will not help you. Well, let's talk about the fourth thing. That's better algorithms. And we saw this idea before when we were doing Euler's algorithm, when we were doing Euler's problem, about Euler's cycle problem. We said, you know what? You tried going through all possible paths. That was okay, you got the answer, but it took you a long time to do it. But here's a better way to do it. Count how many vertices, how many edges come out of each vertex, and then you'll be able to give a better answer to that. So we saw that. So if you can give a better, maybe there's a better algorithm to solve the satisfiability problem. Maybe there's a better algorithm to solve that, and that's what we're going to explore today, whether or not there is. I'll just give you away the hint. We strongly believe there isn't. But okay, so let's talk about that. Okay, so this is the beginning. We want to see whether or not there's a better algorithm. So what I'd like to do is do something that we've never done before. I'd like to change one problem into another problem. Okay, so we never really saw this before. Okay, so we have the set partition problem. Let's remember what it is. Set partition problem is I give you a bunch of numbers. I want you to split them into 2 sets such that the sum of these guys is equal to the sum of these guys. And the subset sum problem is almost like that. What is that? I given a bunch of numbers and a capacity. Find me a subset, just like you're finding a subset here. Find me a subset such that they're equal, such that the sum of all the elements in the subset are equal. Okay. So what I'd like to do is I'd like to show you how we're going to change this problem into this problem. Okay, we're going to change. Now, why we're changing it, we'll see why in a second. Okay, so here's a typical example of such a problem, of a set partition problem, and I want to be able to find 2 subsets such that when you add up all the elements, you get the same thing. Okay. Okay, what I want to do is change this. I don't know the answer to this problem. I don't know if there's a yes or no answer. Okay, if I had more students in here, they would tell me yes or no. So he's some student who's good at it. Okay, but I'd like to change this problem into a subset sum problem. Okay, so here's what I do. And again, there are many subset sum problems, but I want to change this problem into one, and you'll see it has a special thing. So here is the problem. 5, 19, 15, 12, 13, 11, I'm sorry, I made a mistake here. That was a 13, but I had already 13. I want to make that a 7. Okay? So now I'm going to copy the same numbers. 5, 19, 15, 12, 13, 11, and 7. Okay. Now, is that an instance, is that an input to the subset sum problem? No, I'm missing something else. What am I missing? I'm missing a capacity. So here's the idea. I want to find, I'm going to give a capacity here, but I want it to be related to this. So I'll tell you what the capacity is. The capacity is the sum of all, okay, let's write that better, sum of all divided by 2. If I add up all these numbers divided by 2, so the sum of all, if you add up all these numbers, you'll see you get 82. Divided by 2 is 41. Okay, now I ask the following question. So, one second. I changed this problem with the set partition problem into a subset sum problem. Now I ask the following question. Is there a subset of these that gives you 41? Okay, now you stare at it, stop the YouTube, stare at it, stare at it, stare at it, and you'll see the answer is yes. Let me give you the answer. You ready? Here's the subset. 12 plus 13 is 25, plus 5 is 30, plus 11 is 41. Okay? So the answer to this question is yes. Guess what? From this, I can find an answer to this question. Okay, why? Because, let's do it. Well, I take everything in here, 12, 13, and 5. 12 and 13 is 25, plus 5 is 30, plus 11 is 41. Then take everything not in here. Let's see what's not in here. 19 is not in here. 15 is not in here. And 7 is not in here. Let's just make sure this works. 7 plus 5 is 22. 22 plus 19 is 41. This is 41, and this is 41. So notice what we just did. By solving this problem, we can definitely solve this problem. That's the main point here. By solving this problem, we can definitely solve this problem. Let's just see what we did here. I had a problem. I wanted to find a subset. I wanted to find two subsets here that are equal. So what I did was I changed it into this problem, and this problem is good at finding subsets. So I changed it. I gave the same numbers, but here the capacity was exactly half. I made this capacity to be exactly half, so that the answer here will be yes, the answer here will be yes. Okay? Okay? So if I find an answer here, then I'll find an answer here. Great. Good. Let me show you a problem. Okay, so fine. Erase that. You have that in your notes. Let's do another problem. Okay. Let's change this 7 to an 8. Okay, what did I just do? Now notice how many odd numbers we have. We have 1 odd, 2 odd, 3 odd, 4 odd, 5 odd. 5 odd numbers is odd. And in fact, the sum of all these numbers is 82, 83. Okay, so I'm going to change this. C, capacity, is equal to sum of all divided by 2. which is equal to 83. This went from 7 to 8. 83 divided by 2 is, what's the answer? 83 divided by 2 is 41.5. Question: are you going to find a subset of these numbers such that it's exactly equal to 41.5? Absolutely not. These are all whole numbers. Are you going to find a subset of numbers such that two subsets such that are equal? Answer is no. So the answer here is no, and the answer here is no. Okay? But this is just a stupid trick because I made it odd. So that doesn't, that's not. But again, we could try another trick. The main thing we're doing is we're showing that the way we're changing this problem into this problem, if you can find an answer to this problem, you can definitely find an answer to this problem. Let's do another example. Okay, let's do another example. 34, 8, 6, and 2. By the way, all even. So this is definitely, the sum of it is all even. I'm going to change this problem into 34, 8, 6, and 2. Okay, well, 1 second. That is not a problem here because I didn't give a capacity. So let's give a capacity. The capacity is equal to sum of all divided by 2. Let's see what the sum of all is. This is 48, 50. 50. Oh, divided by 2, which is 25. Question: can you get 25 out of here? Everything's even. Can you get 25? Answer: no, you can't. Can you get 25 over there? No, you can't. So if the answer is no here, the answer is no here. Okay? Great. You can try another problem. Pick another problem here, change it into this problem, and see if the answer is yes here, the answer is yes here. If the answer is no here, the answer is no here. Okay? Now, why are we doing this? Why are we changing one problem into another problem? We'll explain it in a few minutes also, but I just want to give you a hint. The idea is as follows. Let's say you have an expert who's great at this. Let's say you have an expert that's absolutely great at these problems. Then look what you just did. By changing this problem into this problem, you can definitely solve. Not only can he or she be very good at solving this, but you can use their experience to solve these problems. Okay, so the idea is as follows, is this problem is easier or equal to this problem. That's the main idea. This problem is easier or equal to this problem. Let me show you why. Because if you can solve this problem, you can definitely solve this problem. That makes this easier than this problem. Let me give you an example. Walking up 3 or 4 flights of steps. Okay? You're in Boylan Hall, you're in Ingersoll Hall, you want to walk up. Here's the idea. If you can walk up to the 4th flight without huffing and puffing, you can definitely walk up to the 3rd flight without huffing and puffing. We talked about this. This is piggybacking, right? So the idea is as follows. If you can solve this problem easily, then you can solve this problem easily. Let me show you how. So again, if you have some expert who's very good at solving these types of problems, then what you do is you take your problem from here, you change it into here, and it's very easy to solve this. Okay? If the person's easy at solving this, then you can change the answer and get the answer for this one too. Which means if this is easily solved, then this is easily solved. There's one other thing here. Let's say this problem is not easily solved. No matter what you do, you're not going to be an easy way of solving this. Well, guess what? Then this problem, it will also not be easily solved. Another way of saying this. Let's say you cannot walk up to the 3rd floor without huffing and puffing. Okay? Then the harder problem, you definitely can't walk up. You definitely can't walk up to the 4th floor without huffing and puffing. Okay? So we have this concept of one problem harder than the other problem. That's what we're bringing in. Okay, let's do another example. Okay, another example of two problems that are very, very similar. Well, in a certain sense. Okay. Hamiltonian Cycle problem. Okay, let's remember what that's all about. Okay. Question. Is there a way, starting from one point, going around, hitting every single vertex exactly once, and hitting and coming back to the original? Okay, that's the Hamiltonian Cycle problem. I can tell you the answer is yes, but before we do it, I want to change this problem into a traveling salesman problem. Okay, so we're going to change this problem into this problem, and by changing it, it's called a, I'll tell you what it's called in a second. By changing it, we're going to show we want to change it a certain way such that the answer to this will be yes if this is yes, and the answer for this will be no if this is no. We want them to have the same answer. Okay, so I'm going to show you how to change this problem into this problem. Okay, first, take the same graph and draw it again. But 1 second, we have a problem here. That's not the typical input for a traveling salesman problem. What do we need for a traveling salesman problem? We need that we can go from any city to any other city with one edge. Okay? Well, yes, I can go from here to here. I can go from here to here. I can go from here, but I can't go from here to here. Okay, and I can't go from here to here. Okay, so I have to add in extra edges. So let's add in extra edges. Okay. Fine. Okay, 1 second, I have to add in another extra edge. Okay, that's another extra edge. Okay, now this is what's called a complete graph. I can get from any vertex to any other vertex. Okay, with only one edge. Okay, good. There's nothing there, so we want to make sure that this is not crossing. Okay, great. Now, is that the input for a traveling salesman problem? No, it's not the input for a traveling salesman problem. The input for the traveling salesman is not only a complete graph where you can go from any city to any other city, any dot to any other dot, but also I need to give it weights. I need to give it values. Okay, so I'm going to give it values. Ready? This edge is 0, 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 this edge is 0. Okay? All the old edges are 0. All the new edges are 1. Okay? Now, question, is that the input for the traveling salesman problem? The decision problem of the traveling salesman problem. Not the optimization. The optimization was where we're looking for the best. I'm not interested in that. We're only talking about decision problems this whole day. We're only talking about decision problems. And the answer is no, we're still missing something. We're missing a number, and we want to know, can you go through all the roads for that amount, yes or no? And the answer is, and you have to give the number, and the number is k is equal to 0. Okay? K is equal to 0. In other words, can I start from any city, go around, hit every single city exactly once, okay, and come back to the original thing using only 0? Let's think of these things as, let's think of them as tolls. These are toll-less roads, roads without tolls. The green ones are, the new roads are, cost me $1. Question, can I do it with costing 0 amount of dollars? And the answer is yes, I can. So let me show you how you do it. It's very simple. You start here, you go like this, 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 and back. I did it. All 0, 0, 0, 0, 0. I come back to the original. I made it. Okay, so the answer here is yes. And you know what? Because I only use the old roads, guess what? The answer here is also yes, because I can do that. So if the answer here is yes, the answer there is yes. Okay, great. Let's do another example where the answers will be somewhat different. So let's go through here. I don't know what the answer is. I don't know what the other example is, but we'll figure it out. Let me find a good example first. Okay, so here's a nice problem, this Hamiltonian cycle problem. Okay, here's a nice input. Can I make a trip, starts any place and comes back to the original? Okay, and I'm going to tell you already the answer is no, but I'd like to show it to you by changing it into a traveling salesman problem. So I'm going to change this into a traveling salesman problem. I'm going to draw the same picture. Okay, but one second, that's not a traveling salesman problem. A traveling salesman problem is where you can go from any city to any other city. Now, this is a Hamiltonian cycle problem. I need that, but here I need to be able to go from any city to any other city. So let's add in roads. So we're going to add this road. I'm going to add this road. Okay, I need two more roads. This one directly. Okay, because I needed to go through two things, and this one directly. Okay, great. Now, is that the input to a traveling salesman problem? No, it's not, because yes, that is a complete graph where you can go from any city to any other city with only one edge, but it's not a traveling salesman problem because you have to add in weights. You have to add in how much money does it cost. So let's add in 0, 0, 0, 0, 0, 0. Okay, one second. But those are not the only roads. How about this? 1, 1, 1, and 1. Great. Now, is that the input to a traveling salesman problem? No. We're dealing with the decision problem. I need to have the same thing. So what I'm going to do is k is equal to 0. Now I ask the following question. Can I make some cycle that starts at any vertex, ends at any, comes back to the original thing, and does it costing nothing? Again, think of the black lines as the old roads, and you put in new roads, but the new roads cost money. I could have made this 1, 2, 3, it doesn't matter. The point is, I want to keep the price 0. I want to remain only using the old roads. Why? Because that's exactly the old roads. Okay? And the answer is, no, I can't. Now, let's just do it without, watch this. Start here, go around like this, go around here, go here, and then come back up here. So, let's do that again. Start here, go around here, go around here. 0, 0, 0, 0, come here. I can't go there because I visited that city already. I can use this one thing, but it would cost me $1. You want to know if I can do it for free? 0. The answer is no. Okay, great. So we changed this problem into this problem. The answer is no here. Guess what? The answer is no here also. Okay, so what did we do? What do we gain out of changing one problem into another problem? Again, what we gain is as follows. We can say the following thing. If there's some expert who can give yes/no answers to this very quickly, then this problem can easily be solved, because changing this to this is what's called a polynomial reduction. A polynomial reduction. We reduce one problem into another problem. We reduce one problem into another problem. We change one problem into another problem. And we do it in a polynomial amount of time. It's very short. Look, all I did was take this, copy it over, add it in the ones, add it in the zeros, add it in the k is equal to 0. It's very simple. But the point is, if there's an expert who can solve this, then this can be easily solved. So again, this problem is easier, or just as hard, we'll talk about that later, or just as hard as this problem. Why? Because if you can solve this problem, you can solve this problem. Now, instead of talking about an expert, let's talk about computer programs. And the idea is as follows. Let's say there's some fancy computer program to solve this in polynomial time. We went through the traveling salesman problem. I showed you that it'll take trillions of centuries to solve some of these problems. Okay? I don't have a better algorithm. But let's say there was a better algorithm. Guess what? Not only would there be a better algorithm for this, there would be a better algorithm for this. Why? Because if I wanted to solve this problem, I would just change the inputs of this problem into this problem, use your better algorithm here, and I'd be able to solve this problem. So if you could solve this easily, if there is a polynomial algorithm for this, guess what? There's a polynomial algorithm for this. Okay, I'll repeat this over and over and over, at least 10 times today, but we'll understand it. Okay, and again, this is a new concept. Changing one problem into another, saying that one problem is hard or just as hard as the other problem. Okay, what we're doing here is as follows. We have problem A. We have a problem. We have problem B. We have another problem. By changing one problem into another problem, look what we're doing. Okay. Damn. Let's say you have a way of solving you have a problem B decider. So this is a problem. I'm not talking, there's a lot of different problems. I don't want to talk about these. But you have a problem D decider. That means you have input to problem B, and you're going to get out, these are decision problems. We're only talking about decision problems, where you're going to get out a yes-no answer. Okay, great. Now, what I'm going to do is, if I want to solve problem A, I'm going to change this, not change it, but I'm going to use this and make a problem A decider. Here's what I'm going to do. Okay, watch what I just did. Now this is a problem A decider. It uses a problem B decider. It's like if you have a fancy computer program that does something, I can take that computer program, put it into my computer, and now I can use it. That's exactly what problem A is doing. So look what I do. I take an input to problem A. This is called a polynomial transformer. I transform it, but I transform it in an easy way. I did this for the subset, for the set partition problem. I changed it into the subset sum problem. It was an easy transformation. I just took the same numbers and I figured out what the capacity was. It took 2 seconds flat. Okay? I have such a problem. This gives me a yes-no answer. And guess what? This is one of the things I wanted to show you. If the answer is yes for the B problem, the answer will be yes for the A problem. If the answer is no for the B problem, the answer will be no for the A problem. If I have such a setup, then I've successfully changed a problem A to a problem B. Now, let's go through it. Let's say I told you I don't know of a polynomial algorithm for the traveling salesman problem, but I'm not the smartest person in the world. Let's say there is somebody who does. If there's a polynomial algorithm for this, then guess what? There's a polynomial algorithm for this, because you just do the transformation, get it out, and this whole big thing can be done very, very quickly. More importantly, if there's no polynomial algorithm for this, then guess what? Then there will not be a polynomial algorithm for this. Okay, so if this is solvable, then this is definitely solvable. And the way we write it is as follows. Problem A is polynomially reducible. That means it's easier or equal to problem B. Okay, and we had two examples of this. We had set partition problem was polynomial reducible to subset sum problem. Okay. We also saw that Hamiltonian cycle problem is polynomial reducible to the traveling salesman problem. Okay, and there are many, many, many more of these. Okay, and again, why are we doing this? Because we want to talk about this problem is easier than this problem, this problem is easier than this problem, this problem is easier than that problem. And if we can polynomial solve this, we can definitely polynomial solve this. If we can polynomial solve this, then we can definitely polynomial solve that. So that's what we're all talking about, okay? But more importantly, let's be more exact. If there was a polynomial algorithm for this, there would be a polynomial algorithm for this. If there was a polynomial algorithm for this, there'd be a polynomial algorithm for this. If there's a polynomial algorithm for this, then there's a polynomial algorithm for this. Okay, great. Very good. Very good. Now, this section, section 5.3 in the book, is called They're All Connected. And this is the idea. The idea is that every single problem can be changed into every single other, all those 5 problems can be changed into each one of them. Now, let's say my favorite problem is the traveling salesman problem. That's a fact. That's not a let's say. My favorite problem is the traveling salesman problem. I always think of different ways. I say, maybe I can solve it. Maybe I can find a polynomial algorithm. Okay? I've been thinking about it for 25 years. Okay? Guess what? Not a lot of success going on here. But the point I'm trying to make is that if I was able to solve the traveling salesman problem, not only would I be able to solve the traveling salesman problem, I would be able to solve the Hamiltonian cycle problem too. And it turns out that all 5 of those hard problems are all interconnected. If you can solve any one of them, you can solve any of the other ones. Okay? Now, what this leads me to believe is there probably isn't a polynomial algorithm for any of them. Let me tell you why. Because if there was, somebody would have found it already. Somebody would have found it. So let me just restate this. Since all these problems are interconnected, they can be changed into any one of them. If you could solve any one of them, you can solve all of them. Hold on. Okay, we need a new definition, okay? So all 5 of those problems that we dealt with are called NP problems, but I want to say something more. They're called, actually, NP, they're something else. So let's find a new definition. Definition, a problem is NP complete. Okay, so we know what NP stands for. NP means it's hard, okay? But NP complete means they're the hardest NP problems. Let me show you what that means. So a problem is if a problem B is NP complete if B is NP. Okay, it's a hard problem, but then it has a killer requirement. 2, and all NP problems C, C can polynomially be reduced to B. In other words, it's the hardest NP problem. Let me just show you a picture. Here's NP. Okay, here's NP. B is NP complete if B is in here. Okay, and any other problem, C, C prime, A, D, D prime, all those other problems in here, they can all be changed into B. What does that mean? Well, that means that B is the hardest problem, because what do we say? We say if you could change it, then if you could solve this problem, you can solve this problem, this problem, this problem, this problem, this problem. That's the definition of the hardest problem. So if B is hard, then you can easily change. If B is NP complete, then all these problems are easier or equal to. It's going to turn. Okay, fine. Okay, let me just tell you one other thing. Let's say I have a problem that's NP complete. That's great. This is a very hard problem. Okay, I wanted to show, let's say I want to show another problem is NP complete. Watch what I have to do. I want to show another problem is NP complete. So let's say I have another problem called B prime. Okay, I want to show this is NP complete. Watch what all I have to do. I have to do is change this problem into this problem, and look what happens. Because all these problems can change into this, and this can change into this, conclusion, all these problems can change into that problem. Okay? And the idea is as follows. Once I have an NP-complete problem, I can easily make another NP-complete problem. All I have to do is show it's harder. Okay? I can show this is harder. Okay, so once you have an NP-complete problem, it's very easy to find other NP-complete problems. Now, the hard part is, how the hell are you going to find the first NP-complete problem? Because I got to tell you, I told you about 5 NP problems. Okay? How are you going to show other things can change into that problem? Now, Joe, just 1 second. This is a book from 1979. Okay, it's 41 years old. 40 years old. Okay, it's called Computers and Intractability: A Guide to the Theory of NP Completeness. It has hundreds, literally hundreds of problems that are NP complete. I only showed you 5 of them, but there are hundreds of problems that are NP complete. So how are we going to show that there's one problem that anything could change into? Okay, so I got to tell you a little Jewish story before we go on. It's a very cute story. It's a very interesting story. You have to know what tongues are. What are tongues? Tongues, not thongs, tongues. Tongues are things that you use for a fireplace or a barbecue. They're like giant scissors where you open and close. Okay, and what are tongues used for? Well, what are tongues used for? Well, they're used to handle hot metal, okay, or hot pieces of wood. If you want to have, you're working with charcoal, or you're working with wood things in your your fireplace or your barbecue, you don't want to touch it with your hands, okay? You want to touch, but you want to deal with it, and the way you deal with it is you have tongues, and the tongues hold on to it, and then you can manipulate it. You can heat it, you can bang it, etc., etc. If you ever watched a martial arts movie, they're always holding the sword. They bang the sword, but they're holding it not with their hands, because you can't hold hot metal with your hands. They're holding it with tongues. Okay, so that's what the tongues are. Okay, question. What are tongues made out of? Answer. They're made out of metal. Okay. Question. How do you make tongues? How do you make tongues? Answer. Well, you have to manipulate hot metal. You have to form it. You have to take metal and you have to form it into something which you can manipulate, which looks like tongues. And tongues are basically you need two pieces. You have to have somehow connected. You have to be able to let them move. Okay, but they are doable. Question: how do you make tongues? Answer: you need another tongues to make a tongues. It's a very strange thing. You need tongues to make tongues. If you don't have tongues to make tongues, you're not going to be able to get another tongues. Okay? So, question: how do you get that earlier tongues? You must have had some tongues beforehand. Okay? And this goes on and on and on. Question: who made the first tongue? Okay? It's a complicated question. Who made the first tongues? Okay? And so there's a Jewish legend that deals with this issue. And the legend says that God, after he created Adam and Eve, he made tongues, because without tongues you cannot have tongues. Okay, so there's no way a person can make tongues, because tongues are made out of metal, and you have it. And so it has to be, only God can make it, the original one. That's the legend. Okay. I don't want to deal with it in any way or sense of more, but the question is as follows. I know, given an NP-complete problem, how to get another NP-complete problem. But how do I get that first NP-complete problem? How do I make that first NP-complete problem, which is harder than any other NP problem? How do I find that? Okay? And that is what is the content of something called the Cook-Levin Theorem. Okay, so let me tell you about this. This theorem goes back to the 1960s. Stephen Cook is Canadian, but we call him a North American because we want to have him. Levin was a Russian, but he now lives in America. He's still alive. They're both still alive. Okay, and they proved this theorem. They were totally independent of each other. One was in Canada, one was in Russia, but they proved the following theorem. You ready? Satisfiability is NP complete. Okay. They were able to find the first NP complete problem. And the reason why they were able to do it is because they thought about what, and I'd like to show you what they did. They said, look, you want to show that every single NP complete problem can reduce to something, and I mean every. This has thousands and it's 40 years old. There's millions of such problems. Okay, they show up all over. Okay, great. You want to show that? Well, tell me, what do all these things have in common? Answer: they are all computer problems. Question: how does computers work? How do you work with computers? What are computers? Answer: computers work with logic. They are engines of logic. You say, if I press this, then I should do that. If this is on and that is on, then you should do that. If the guy is pressing this button and that button, then do this. If the thing is playing and he wants to go higher, then implies this, etc., etc. They're all logic. So what these two guys said, Stephen Cook and Levin, showed was all these problems can be changed, because they're computer problems, they can be changed into logic problems. And with some fancy manipulating, they showed that satisfiability, if all these problems can be changed into logic problems, well, satisfiability deals with logic. Okay, I'm going through details a little bit too quickly here, but you're not responsible for all of them. But the point is, logic any problem can be changed into a logic problem. That's the main point. Any problem can be changed into a logic problem. In fact, that's exactly what your computers do. They take any problem and they change it into a logic problem. Okay, so Cook and Levin showed that there's one definite problem that is satisfiability. That's an NP-complete problem. And they found that all the other problems can be changed, can be reduced from SAT. Okay? In particular, the 5 problems that we saw, SAT is already NP-complete problem, but the 5 problems that we saw, namely the traveling salesman problem, Hamiltonian cycle problem, subset sum problem, set partition problem. All those are examples of NP-complete problems. Okay, so all those are examples of NP-complete problems. Great. And the answer is, if you can solve any one of them, you can, by solve I mean find a polynomial algorithm. If you can solve any one of these, if you can find a polynomial algorithm for any one of these, then you can solve all the NP problems. Okay, hold on. Okay, so how is this going to help us? Now that we have this concept of a problem that can be solved, how is it going to help us? The hardest NP problems, how is it going to help us? It goes as follows. P is a set of all problems that can be solved in polynomial time. Okay. NP is a set of all problems that can be solved with an exponential or factorial amount of time. NP is those problems that can be solved within exponential or factorial amount of time. Now, polynomials are smaller than exponential and factorial. Okay, that was that thing from page 118. So, NP problems are for sure can be solved within P problems can for surely be solved in NP problems. Another way of saying this is P is a subset of NP. Let me say it another way. Easy problems can be solved in a long amount of time. But now we have to ask another question. Here's the other question. Question. Is P equal to NP? It looks like this is a subset of this. But question is, are they in fact equal? Okay? Is one yes, we know one is a subset, but maybe they're equal. Let me just give you a feeling of why you might think that they're equal. Remember I showed you Euler's cycle problem. I showed you Euler's cycle problem and I said, oh look, how do you do it? And you didn't know. Well, you know what? Maybe there's a trick. Maybe there's a trick. So and I showed you there was a trick. I said, look at every vertex, look at the things coming out of the vertex, are they odd or even? If they're all even, then you do the following. If there's all but two are even, etc., etc. So there was a good trick, and we used that trick. That trick was a polynomial trick. Conclusion, Euler's cycle problem is a polynomial problem. Great. We had 5 hard problems. Maybe there's a trick. And if there was a trick, if there was some trick, a polynomial trick, then all 5 of those problems would be, you would think all 5 of those problems are over here, but no, if there was a problem, they would all become polynomial. All of them will become polynomial. So, now we're asking the same question. We know P is a subset of NP, but maybe they're in fact equal. They would be equal if there is a trick. So, we started off asking this in the beginning of this section. We said, you know what? Faster computers, multiprocessors, quantum computers, all that will not help us. But maybe better algorithms will. Maybe there's a trick. So we asked the question again, is there a trick? Okay? And that's called the P equals NP problem. The P equals NP problem. Okay? The P equals NP problem is the hardest computer problem around. And there's a million videos on YouTube about it, and it's worth spending some time thinking about it. And it basically asks the following question. Are there any tricks that would make us solve the hard problem, that would make us be able to solve the seemingly hard problems in a short amount of time? Now, most people believe no, there is not a trick. Most computer scientists say no. This is the way it is. P is a subset of NP, and they're not, and they don't equal. Okay, but there are some professors who say no, P actually is equal to NP. I don't know the trick, but there are tricks. The tricks exist somehow there. Okay, or they would say they don't know the tricks, but they would say the tricks somehow exist. Okay? Now this question of whether or not there are tricks is called the P is equal to NP problem. It's a very hard problem. No one knows how to solve it. It's been around since the early 1970s. Again, in 1960s they found this concept of NP complete, and they said, okay, now let's see, what can we do with that? Can you solve any of these NP complete problems? If you were able to solve any of these NP complete problems, all the problems would be solvable and they would all be NP. Okay, so you have two possibilities. P is a proper subset of NP, or P is equal to NP. Okay, now for the first time in this class I'm going to tell you what I personally think, although that's not important, but I think this is true. Most people think this is true. This doesn't seem true. In other words, there are no tricks. In other words, all those hard problems, not only can't they be solved with faster computers, quantum computers, multiprocessors, they probably don't have better algorithms either, which means there are inherent limitations to our knowledge. We cannot solve these problems, even though they're easy to state, but we can't solve them. Okay. In the year 2000, there was a man named Clay, who started an institute called Clay Institute. Okay, and it was a millennium, and he wanted to promote mathematics, so he made the following thing. Him and a bunch of experts chose 7 hard math problems, and he said if anybody can solve any of these 7 hard math problems, he will give them $1 million just to promote people to start doing it. One of those problems, I don't want to go through all of them because I don't know all of them, but one of those problems is the P equals NP problem. He said, if you either show that there's a trick or show that no trick exists, I'll give you $1 million. Okay? And people have been working on it. People have been working on it since the 70s, but people have got, even more excited about it since the year 2000. But no one has found a solution. No one can prove either this or this is the right way. Okay? So I'd like to show you how you can make $1 million. In fact, I'll show you how to make $1 million. But before I show you how to make $1 million, so you have to do one of these two things, but I'll show you how to. Before I do it, there was one problem that was on this list. Called the Poincare conjecture, and that was solved. It was solved afterwards. The man who solved it, his name is Gregory Perelman, okay, and he solved the problem, but he didn't accept the present. He said we don't do mathematics for money, and so he didn't accept the $1 million. Okay, but if I solve this problem, I would accept the money because I have to pay a mortgage in a Brooklyn house. So I would accept the money. Okay, but the point is, this problem was already dealt with. Okay, so nobody's working on this problem anymore, so they're working on the 6th problem. So if you're going to solve this problem, you better do it fast. So that's why I'm here. I'm here to tell you how to solve this problem. There's one of 2 ways of solving it. Okay, either way you do it, you'll make $1 million. So let me tell you the 2 ways of doing it. Okay, one is show that this is right. Show that P is equal to NP, and that's very simple. You already know how to do it. Pick any NP complete problem, and there are thousands of them, but you can pick any of the 5 that we did, and go and find a polynomial algorithm for any one of them. Go and find a polynomial algorithm for any one of them. Boom, you've solved the problem. Okay, so pick an NP complete problem. Let's say the traveling salesman problem, my favorite, or the subset sum problem. Find a polynomial algorithm that solves it without going through all possible routes, without going through all possible subsets, without going through all possible lines on the truth table. Find one. And then, if it's polynomial, since those are the hardest problems, all the problems become P, you're very, very happy. You make $1 million. Okay, that's the easy way. It's probably not true because it probably doesn't exist such an algorithm, but that's okay. Okay, here's another way. You ready? Pick any problem that's an NP problem, not even NP complete. Pick any problem that's out there, okay? And all you have to do now is prove, here's a hard problem, prove that no polynomial algorithm can solve this problem. Now, we never did this before. We always said, oh, let's try to find a better algorithm. Let's try to find a polynomial. Let's do a trick. Let's look for a trick. What you have to do here is prove that no trick exists. If you can prove that no trick exists, I have no idea how you do that. How do you prove? It's very easy to prove something exists. How do you prove something does not exist? I can prove that exists a pink elephant. I just bring a pink elephant. Bring the pink elephant. Nah. Okay. Bring a pink elephant in here. How do I prove that no pink elephant exists? Very hard. How do you prove that no algorithm exists? I have no idea. Okay, that's why it's worth $1 million. Okay, so if you do either one of these, prove that this is here and not in here, or prove that this is polynomial, then you make $1 million. Just want to show you how to make $6 million. Because I already showed you how to make $1 million, but when you make $6 million, you should really remember your beloved professor. I want to show you how to make $6 million. The way you do it is as follows. One of these two things are true. I personally think it's this one, but it's harder to do. Well, they're both impossible, so it doesn't matter. But let's say you prove this. Well, one of the NP complete problems is the following. Given a math theorem, find a proof for it. Okay, I don't want to get into this because it's just a side thing, not very important. Given a math theorem, find a proof for it. It's very hard to prove theorems in math, okay? But it would be nice to have a computer program that does this. And there are computer programs that do this. The only problem is to find a proof for a particular theorem, it takes exponential amount of time. It takes a humongous amount of time. So given a math theorem, find a proof for it takes a tremendous amount of time. In fact, it's an NP complete problem. But let's say so it is an NP problem. Let's say you were able to do this. You were able, not do this, but you were able to do this. You were able to find a polynomial algorithm for the traveling salesman problem, for the Hamiltonian cycle problem, for the subset sum problem, for any of the 1,000 problems that there are. Then this problem would also have a trick for it. And this problem would be polynomial also, because there wouldn't be any NP problems. All the problems would be polynomial. So this hard problem would become easier too. So here's what you do. Take this, okay, and then go through all of Mr. Clay's things, write them down as a math theorem, put them into that program that you have a polynomial algorithm to solve this, and solve each and every one of those. You won't get $1 million just for proving that P is equal to NP. You'd get $6 million because you have 6 problems open there. And you would be able to find proofs for them in a polynomial amount of time. Conclusion, you would make $6 million. You see how wonderful this class is? Anyways, alas, I don't think this is true. I think this is true. But if this was true, not only would you make $1 million, you'd make $6 million. Great. That is the end of section 5.3. Let's just finish off the chapter. The chapter has a little bit more to go, and I'd like to show you. Okay, so a little bit more to go. And so let's do section, oops, wrong pen, sorry. Section 5.4, solving problems approximately I'm not sure if that's the title, but it goes as follows. It goes as follows. You ready? These problems that we showed you, the 5 problems and the thousands of other NP problems, they show up every day in business. They show up in the real world. Let me just give you an example of where they show up. Take the traveling salesman problem. We all live in Brooklyn. We have school buses. School buses is an example of the traveling salesman problem. A bus driver has to go to certain corners. He has to pick up the kids at certain corners. He wants to do it as quickly as possible. He wants to optimize that trip. Okay? How does he do it? How does he optimize that trip? Okay? So that is called, so great. So we know that it's very hard to do. We know, let's say he has to make 30 stops. That's extremely hard. We have no way of doing that in a finite amount of time. We have no way of doing that. 30 factorial is a humongous number. Okay? There's no way to do that in a finite amount of time. Question, is there something else we could do? And the answer is yes. Approximation algorithms. Approximation algorithms. What we're going to do is we're going to solve the problem a little bit in the following sense. We're going to try tricks, okay? And what we're going to do is we're going to get a solution. The solution won't necessarily be the best solution, but it'll be kind of close to a good solution, okay? And more importantly, we can find this solution in a polynomial amount of time. Conclusion, we would be happy. Okay, so we're going to do 2 examples of approximation algorithms, and we'll see how it works, and you'll see it's a very nice area. Okay, so the first thing we're going to do is for my favorite problem of all time, the traveling salesman problem. So let's find an approximation algorithm for the traveling salesman problem. Imagine the following. Okay, you have a bunch of cities in the United States or something, and you want to visit every one of them. Okay, now you can say the distance from here to here, the distance from here to here. You can look at, this is not really a graph, but it doesn't matter. You can imagine that the distances are the actual distance on your map. Okay, and so you want to know the shortest possible route. The way we're going to do this is something called the nearest neighbor heuristic. I probably didn't spell any of these words right. The nearest neighbor heuristic. The nearest neighbor heuristic says as follows. First of all, the word heuristic means it's kind of like a rule that sometimes is true and sometimes is not true. So it's a rule that we sometimes think is true and sometimes we think it's not true. It's usually true. Okay? Okay, so here's what the nearest neighbor heuristic says. Here's how to solve this problem. What's the problem? We want to find a route that starts someplace, shortest amount of distance, goes to every other thing. Okay, so great. So let's start here. Okay, I need a measure. Okay, the nearest, so now here's what you do. Look around at all your cities, find the nearest city you did not visit yet. So the nearest city here is this one. Okay, great. Now, you follow this rule again. Question. What's closer, this or this? I think this is closer. Okay. The nearest city, unvisited city, is this. The nearest unvisited city is this. The nearest unvisited city is this, 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 this. Okay? So that is the nearest neighbor heuristic. It says try to do that. Now, that's not very hard to do. A computer can do this in a second because it doesn't have to calculate all possible routes. All it has to do is, at every point, look around, see what's not visited, see what the distance is, go to the nearest thing. Very easy. Okay? Can easily be done. I'd like to do another example of this. Okay? We'll do another example. Hold on. Because this was a little bit too easy. I'd like to show you something else. Let's see. I didn't think this one through. Okay, let's see. It might work, might not work. Let's start here. We'll start here. I'm going to look for the nearest city. Actually, hold on. It's hard to take notes with this, I'm sorry. I'm going to start here. The nearest city is here. The nearest city is here. The nearest city from here is here. The nearest city from there is this one, this one, this one. Okay. The nearest city from here is this one, this one, this one, this one, this one, this one, and then this one. Okay? Sometimes it works, sometimes it doesn't work. I'm not saying it's the best possible solution, but I'd like to show you an example where it's not the best possible solution. We're going to do that. The example's in the book, and it's in section 5, and you can read it, but it's a cute little example that I made up. It goes as follows. You have a city here. The distance from here to here is 1. Oops. Let's just make sure we have the numbers right. The distance from here to here is 2. The distance from here to here is 4. The distance from here to here is 8. And the distance from here to here is 16. Okay, sounds good. Okay, let's see how the nearest neighbor will take us. We'll say start here. The distance from here to here and from here from these cities are all on a straight line. Strange, but fine. They're all on a straight line. Okay? Well, what will the nearest neighbor heuristic tell us? It'll tell us go here. Great. Now, let's look at this. The distance from here to here is 3. The distance from here to here is 4. So we should go to the 3 because we always go to the closer one. Now, the distance from here to here is 8, but the distance from here is 3 plus 1 plus 4 is 7, so we go here. Okay, great. Next, the distance from here to here is 16, but the distance from here to here is 8 plus 2 is 10, plus 1 is 11, plus 4 is 15. We go here. Now, we go all the way here. Now, we go here. Okay? And if you add that up, you get something like, you don't have to add it up, because I added it up for you, you get 78 miles. 78. However, it was a stupid way of doing things, because what you should have really done is as follows. You should have started here, go like here, and then go all the way here, come back here, come back here, and come back here. Okay? You could see it. That's with the black magic marker. That is much faster. You're not going backwards and forwards, backwards and forwards, backwards and forwards. Anyways, if you do that, and we talk about it in the book, that is 62 miles. So it's better to do the 62 mile rather than the 78 mile. The point is as follows. The nearest neighbor heuristic will help you solve a problem, but it won't give you the best solution. It'll give you a good solution, but not the best solution. Just a little cute little story. When I was younger, not when I was younger, when my daughter was younger, I used to wait for her. She was on a school bus, and she would go to day camp in the summer. And I would wait for her, and I would pick her up. Anyways, it was a hot summer, and the first day of day camp, I was sitting in the corner where they told me to wait, on Avenue J, whatever. I was waiting and waiting and waiting, and she did not come. She came 45 minutes after she was supposed to come. Anyway, so I asked the bus driver, I said, what's going on? So he said, you know, I have a route here, and the way I made the route, your daughter is one of the last people on the route. So I said to the bus driver, I said, you know, I know how to deal with these things because I told you my favorite problem is the traveling salesman problem. In particular, I know a lot about approximation algorithms for the traveling salesman problem. Here's one, nearest neighbor heuristic is one, but there are a lot more. And I said to him, I said, maybe you can show me your route, and I can find maybe a better route. So he had nothing to do. In fact, most of the girls were the students were let go. So he said, sure, here's the route, and here's what I did. Anyway, so I looked at the route for like 10 minutes. We were talking, and I was looking, and we were talking, and he was, you know, telling me how hot it is, and my daughter was pulling me. She wanted to go home, but I was looking at the route. And I told him some tricks that he can do. The next day, oh, by the way, while I told him the tricks, I also showed him that he should drop my daughter off the 3rd, not the 30th. So my daughter was finished. The next day, my daughter was there 10 minutes later, after the day camp was over. The next day, I brought my daughter to school, and then the bus driver was thrilled. He said, the next day he told me, he said he was absolutely thrilled. He said, my way of doing it saved him a good 20 minutes on his route, which was very, very helpful. He was very happy for it. The next day, I brought my daughter to school, and all the other bus drivers were standing there waiting for me to give me their routes so that I can use some of these tricks to help them, you know, finish quicker. Okay, so the nearest neighbor heuristic is one example of a trick that solves an NP-complete problem. I'd like to show you one more. It's a very clever little problem. It's done in the book, and it'll take a minute. Let's do the set partition problem. As we know, that's an NP-complete problem. It's very hard to do, but I want to show you a trick of how to do it. Okay, and it goes as follows. Take a bunch of numbers. 15, 12, 21, 7, 3, 8, 5, 19, 27, 16, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you know what? One, two, three, 4, 5, 6, 7, 8. We did 8 already, so let's do 18. And we did 10. Okay. Here are lots of numbers. Okay? Now, I want to teach you the trick. The trick is as follows. First, sort the numbers. So let's do it. 5 is the first. 27 is the next. 3 is there. 7 is there. So let's do 3, 5, 7, 8 is there. Let's see what's left. 10. Let's put 10. No, there's no 11, so we'll do 12, 10, 12. Da, 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 da. 10, 12. 14 and 13 is not there. 14 is, 15 is there. 16 is there. 18 is there. 16, 18, 15. Okay, 19 is there. 27 we have already. And 21. And that's it. Let's just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Great. By the way, I have no idea if there's a solution here, but let's go through it. Okay, next. Remember the story with Gauss, the little boy Gauss? What did he say? He said instead of counting the numbers 1, plus 2, plus 3, plus 4, plus 5, etc., he said count the extremes. Count the lowest to the highest, the second lowest to the second highest, the third lowest to the third highest. Add them together. So watch what I'm going to do. Okay, I'm going to take the 3 and the 27, add them together, you get 30. I'm going to put them there. So I'm going to add 3 and 27 here. Great. Now I'm going to take the second highest, 5 and 21, and I'm going to put them here. 5 and 21 is 26. I'm going to put them here. 5 and 21. Great. Then I'm going to take 19 and 7, which is 26. And I'm going to put them here. So 19 and 7 goes there. Great. Then I'm going to take 8 and 18. 8 and 18 is what? 26. Isn't that interesting? 8 and 18 is 26. Good. Next. 10 and 16. Sorry, 8 and 18 goes there. Okay. 10 and 16 goes there. So 10 and 16 goes there. Great. Next. 12 and 12 and 15, that's going to be 27. That goes there. I'm sorry, 27 goes there. So what's less? 12 and 15 goes here. I messed up on my accounting here, which is pretty bad. So 12 and that goes here. 27 goes here, but we missed this. What's this? This is 26. 16 and 10 is 26. Okay, great. So, let's see, how much are in here and how much are in here? Okay, and the answer is in here is 26 and 26 is 54. So 54, 26 and 26 is 54. 25. 26 and 26 is 52. And 30 is 82. Okay, and this is 26 and 26 and 27, so this is going to be 3 less than that, so that's 79. So this is 79, and this is 82. Not bad. Not very good, but not bad either. Okay, so again, I'm not sure that they can be done properly, but that's a quick way of getting somewhat close to an answer. It's not going to be the best answer. It's not going to be exact, but it's going to be close to it. So those are approximation algorithms. And again, approximation algorithms are used all the time because you need them because businesses have to solve these problems. And if you're a programmer, you really have to deal with these issues right away. Okay, great. That is section 5.4. Okay, Let's just 5 more minutes and we'll finish off section 5.5. It goes section 5.5, even harder problems. Okay, so let's go through it. We had 2 to the n and n factorial are very hard. But there's a lot harder problems than that. For example, 2 to the 2 to the n. Okay? Now, I just want to show you how hard this of a problem this is. If you plug in the number 4 here, you get 2 to the 2 to the 4. Okay? 2 to the 2 to the 4, let's see, 2 to the 4 is 16. So 2 to the 16 is, I think 64,000, something like 64,000, around 64,000. That's humongous. So we talked about problems like this and like this, where if we plug in 100, it's unbelievable. Well, if you plug in just 4 over here, you already get large numbers. God forbid if you plug in 100 here, it would just be mind-bogglingly large. Okay? Let me just show you some other things that are harder, and there are problems that are this hard. For example, we saw 2 to the n is very hard. How about this? N to the n. Okay? And just plug in the number 10. 10 to the 10 is a humongous number. It's in the billions, trillions, whatever. Okay? So those are very hard. These are problems that are very hard. So again, for every problem, we saw that there's some function that describes how complicated they are. We dealt with these and polynomials. Polynomials were easy, but these. But there are worse things. For example, let's do this. N factorial factorial. Let's plug in an easy number. Ready? 4. That's an easy number. Okay? Let's figure out what that's equal to. 4 factorial is 4 times 3, which is 12, times 2 is 24. So this is equal to 24 factorial. 24 factorial is in the billions, the trillions, and that's just a small input of 4. So there are problems which are even harder. I mean, we could try something like this, 2 to the n factorial. Okay? Again, plug in 4, you get 4 factorial is 24. 2 to the 24 is in the billions. Again, small inputs for such problems already are unfeasible, can't be done. We saw for these problems, you plug in 100, you won't get anything. But even for these problems, even if you plug in smaller numbers, you just won't get anything. Okay, let me tell you one other place. Again, this is a very easy section to read, and you should read it. P-space. The whole time we're talking about how much work, how much time things takes. But you know what? There's another way of measuring things, and that's how much work, how much space it takes to calculate things. So for example, you do your taxes. How complicated, if you're a student doing your taxes, you can do your taxes in 15 minutes flat. You have something called the 1040 EZ. It's a half a page of calculations, how much money you're making, how much how much school you're in. You can do all the calculations. As your life gets more and more complicated, you have to do more and more taxes. And you have to fill out more and more forms. Okay, same thing with here. Instead of looking at problems by how much time it takes, look at problems by how much space it takes to calculate the answers. And that's what p-space is all about, polynomial amount of space. Now it turns out, and you're going to read more about this, that games are things that take a tremendous amount of space to calculate. Think about chess. If I'm playing someone else, a game of chess, how do I do it? Well, I have to imagine what moves I should make, which my opponent will make other moves. I have to look at all the possible moves that he will make against me. But what is he thinking about? He's thinking about all the moves that I make. And I'm thinking about all the moves that he makes. So there's a giant tree of possible moves that can be made. Okay, and in order to do that properly, in order to play games, people playing with each other, okay, people playing against each other, it takes a tremendous amount of memory to do that. Okay, and that's what some of the games are p-space. P-space is even harder than P or NP. NP, remember P is the easy ones, NP is the hard ones. P-space is even harder than that. Okay, so computer scientists spend a lot of time discussing how hard certain problems are. Can they be done? Can they not be done? Great. And there's a little bit more details about this worthy of going through this at the end of chapter 5. But let me just summarize what we saw about chapter 5. There are certain problems that are extremely easy to do. We spend a lot of time with computers. We deal with problems that can be solved very easily. We love computers. We have our cell phones. We play with computers all the time. They make our lives in some sense a lot easier. But what we're pointing out is there are certain problems that just take a tremendous amount of time or space to calculate. Okay? And again, what we showed was these problems are not just, they're hard problems, they are totally unsolvable problems in the sense that no human beings can possibly do it. Okay, in a reasonable amount of time. Now, we're going to move on to chapter 6 next time. Well, let me just give you a foreshadow. Chapter 6 is not about problems that are very hard to solve. Chapter 6 are about problems that cannot be solved, period. Not they cannot be solved unless you wait 42,000 trillion centuries. No, they cannot be solved. There is no solution to them whatsoever. So it's a little bit further away from our knowledge. Not that it would take us trillions of years to solve, which we don't have, but no, they cannot be solved at all. And we're going to spend a lot of time on that on chapter 6. Take care. It's been great.